Hello folks, I am Georgios Papadopoulos and welcome to this video on Internet of Things protocol stack. In this video, we are going to be talking about the evolution of the Internet Protocol suite for Internet of Things. Now, this video is just one in a much longer series of tutorial videos on Internet of Things. So if that interests you, you should subscribe and check out the rest of the videos as well. Okay, first things first. What is the Internet Protocol suite, commonly known as TCP/IP? Well, it is a framework for organizing the set of standardized communication protocols used on the Internet and computer networks. Here is the original TCP/IP model. It consists of 4 layers: application, transport, internet, and link layer. And it is numbered from the bottom up, but the direction depends on if the device is transmitting or receiving a packet. The Internet Protocol suite evolved through research and development founded over a period of time. In this process, the specifics of protocol components and their layering changed. Thus, one of the evolved versions is the TCP/IP protocol suite that comes with 5 layers. In this version, there is one extra layer and one renamed layer. As it can be observed, the original link layer has been split into data link and physical layers. And the internet layer has been renamed to network layer. Now, if we compare 5 layers TCP/IP protocol suite to the OSI model, which consists of 7 layers, the application, presentation, and session layers are illustrated as application layer in the TCP/IP model. In the rest of the video, we will focus on the 5-layer TCP/IP protocol suite. So let's remind ourselves about the protocols at each layer. At the application layer, we have the HTTP protocol among the others. Then the 2 most common transport protocols are TCP and UDP. If TCP is employed, then the source and destination port numbers, sequence numbers, and few more bits of information are included in this layer. At the network layer, we have either the Internet Protocol version 4, IPv4, or IPv6 source and destination addresses. The routers operate at this layer. Next, at the data link layer, we have the Ethernet or Wi-Fi technologies, where the destination and source MAC addresses are included. The switches and access points typically operate at this layer. Finally, we have the physical layer or layer 1. This layer is most closely associated with the physical connection between devices. Basically, once the data arrives at the physical layer, it is then physically transmitted. IEEE 802.3 defines the physical layer and data link layers media access control protocols of wired Ethernet, while IEEE 802.11 specifies the set of MAC and physical layer protocols for Wi-Fi. Now, on top of the HTTP, there is typically very verbose web representation formats such as XML or JSON to structure the information. It is worth mentioning that the protocols at the 2 bottom layers are being standardized at the Institute of Electrical and Electronics Engineers, or IEEE, while the protocols from layer 3 and above are being standardized at the Internet Engineering Task Force, or IETF Standardization Organization. Now, by employing this 5-layer TCP/IP protocol suite, 2 or more typical computers may communicate to carry data from one to another. However, one issue with this protocol suite is that it has been designed for Ethernet and or Wi-Fi based technologies that come with high bandwidth and packet sizes of maximum transmission unit MTU in the order of 1000 plus bytes, which is not realistic for Internet of Things. So what this looks like when we go from the classical TCP/IP enabled devices and networks to a constrained devices and low power and lossy mesh networks such as Thread and 6TiSCH that are based on IEEE 802.15.4 technology for the data link and physical layers, and which come with limited bandwidth and support packet sizes in the order of 100 something bytes. Well, in order to anticipate this transition, IETF has designed and defined a specific protocol stack, often called the 6LoWPAN protocol stack. This newly defined 6LoWPAN protocol stack uses some of the existing protocols, such as the UDP instead of TCP, for the sake of simplicity. Then IPv6 instead of IPv4 is employed, since there are not enough IPv4 addresses left. However, since the IPv6 header is much larger than the one of IPv4, a new adaptation layer 6LoWPAN was defined to compress the IPv6 header and, if necessary, to fragment the packet into multiple frames of 127 bytes. Furthermore, 6LoWPAN compresses the 8-byte UDP header as well. You can find dedicated videos on 6LoWPAN technology on our channel. On top of UDP, the core working group at the IETF has defined the compatible with HTTP and efficient Constrained Application Protocol, or CoAP, which is a web transfer protocol with low header overhead specifically designed for constrained nodes and networks. The interaction model of CoAP is similar to the client-server model of HTTP. Now, if you want to have a detailed overview on CoAP, you should check out the dedicated videos on our channel. Finally, on top of the CoAP, there is CBOR, which is a binary data serialization format loosely based on JSON. CBOR stands for concise binary object representation. In the near future, we do plan to have a dedicated video on CBOR, so please stay tuned. Now, combining the CBOR, CoAP and 6LoWPAN protocols, we can get overheads down to just tens of bytes, which can be carried in constrained mesh technologies such as Thread and 6TiSCH that come with MTU of 127 bytes. This 6LoWPAN stack works well for constrained devices and networks. However, it is not applicable for ultra-constrained long-range LP1 technologies such as LoRa and NB-IoT that support packet sizes in the order of tens of bytes. Towards the same, at the IETF, a new working group was established called LP1, which stands for IPv6 over Low Power Wide Area Networks. The objective of LP1 working group was not to design a new protocol stack in order to avoid potential interoperability issues. Therefore, what was done was to extend the 6LoWPAN compression and fragmentation mechanisms that was previously designed for low power and lossy mesh networks to LP1 technologies. More specifically, the idea was to further improve the header compression performance down to few bytes, and in addition to IPv6 and UDP, to compress the CoAP header as well in order to enable MTUs in the order of tens of bytes. And this was achieved thanks to SCHC protocol, which stands for Static Context Header Compression. And SCHC is a packet-oriented, in other words, flow-independent and generic framework, since it can be applied to other protocols in addition to IPv6, UDP and CoAP. You can find a dedicated video on SCHC fragmentation mechanism on our channel. And that's all, folks. Thank you for watching, and if you have enjoyed this video, you should subscribe and check out the rest of the videos on Internet of Things.